So here we are, 250,000 subscribers, and I just wanted to say a massive thank you to each and every one of you who've watched the videos, subscribed to the channel, shared the videos, left comments. Thank you so much, because we could not have achieved this without you. And yes, I did disappear for a while, but I just want to let you know that I am back, and I have more to say about that later. Today's video is going to be a little bit different because, well, number one, I'm appearing on camera for the first time. Hello. And I want to answer your questions. So thank you for sending through so many good questions. A lot of those questions related to my backstory, my personal journey. How did I get into physics, and how did I end up making these videos on YouTube? So I'm going to start with those kind of questions, and then we'll move into some of the physics questions. So enjoy, let's get going. Tell us your story, why you studied physics, and how it is being a physicist. We'd like to know more about you and your academic path. So I suppose my journey began when I was a child. I was always fascinated by the natural world, and in particular, I had a fascination with space. So I remember as a young child going into bookshops, and I used to just love finding those books which you could open and see pictures of galaxies, planets, and it just made me think, all of these things exist in our universe, but I've never seen them directly, and I was fascinated by this hidden realm. And then I suppose a pivotal moment came around age 14 or 15 when, for my birthday, I was bought the illustrated guide, or the illustrated version of Stephen Hawking's Brief History of Time. And I remember like painfully going through line by line, chapter by chapter, trying to understand this book, which was way over my head. I didn't understand any of it. But I just found it so fascinating to think that there were these fundamental building blocks that underpinned everything that we observe in the natural world. And I remember also trying to go to school and explain what I'd been reading about to my friends. And I suppose that's when I first discovered the joy of sharing ideas. The idea that you could read something, try to understand it, and then try to articulate that to someone else. And then they would get excited about what you were talking about. That then led me to study physics and maths at A level. And for those of you in America, that's 17, 18 years old. And then I went off to University of Durham, to study physics. And that was a 4-year integrated master's degree. So I remember vividly starting my degree program. And in that first year, I had a lot of labs, and they always seemed to be scheduled for 9 a.m. And I struggled to engage with labs, if I'm perfectly honest with you. So at the end of my first year at university, I switched my course to theoretical physics. So that basically traded all of the labs for additional maths modules, and I was far more satisfied with that. But if I'm perfectly honest, I didn't work hard at all during my first 3 years. I messed around, I didn't really go to lectures, and I missed out on a lot of those opportunities that you get when you're at university. However, as I was going into my final year, I got a project supervisor, so I did my final year project, and I picked a project which was titled Einstein's Equations from String Theory. And I knew nothing about Einstein's equations, and I knew nothing about string theory at this stage. But I was fascinated by the topic, because the topic was, can you derive Einstein's field equations of general relativity from string theory? And the project was trying to show how they naturally emerge. And so I was encouraged to go to some grad lectures in quantum field theory and general relativity to just try and piece together some of the prerequisite knowledge so that I can understand the papers that I needed to read for that project. But I loved my supervisor, we got on really well, he was really enthusiastic and he believed in me, and I made very good progress on that project. And then around Christmas in my final year, he suggested that maybe I apply for PhD positions. And I ended up doing a PhD in London for 4 years at the Centre for Research in String Theory, which is at Queen Mary, University of London. And that was an incredible experience. Over those 4 years, I learned a huge amount, and I worked with some fantastic colleagues. It was challenging, don't get me wrong, very, very difficult. I doubted myself continuously, but I managed to somehow get some publications out of that experience. And the last 6 months of my PhD, I actually spent in India, in Mumbai, at the Tata Institute for Fundamental Research. And this is without a doubt one of the most incredible experiences I've ever had, because I was in a completely new country, never been there before. surrounded by amazing people working at this premier research institute. And I suppose what that experience taught me was what I considered hard work was not hard work when I compare it with what I was seeing in the students in the research institute in Mumbai. But I learned a huge amount, had a great time. And at the end of that, when I completed my PhD, I had the possibility of going and doing some postdoc positions in theoretical physics. But if I'm perfectly honest, after 8 years of specializing and specializing and specializing, becoming more and more refined in what I was studying, I felt like my interests were a bit too broad at that stage and I didn't want to narrow it so much. And I didn't really have an alternative. I didn't know what else I wanted to do. So I ended up being a high school teacher. And that's when I fell in love with teaching, because I realized that if you're in front of a group of people and your job is to try and explain the laws of the universe to the next generation, then not only is that incredibly rewarding, but it's also very challenging. I used to love teaching 11, 12, 13-year-olds because they'd have no filter and they'd ask you the first thing that came into their head, really good questions. And it would keep you on your toes, because the challenge I set myself is, am I able to give an honest, correct answer to this question, but translate it in such a way that I don't have to rely on mathematics to do so? And so I learned a huge amount about explanation and the power of explanation during my time teaching. And then I was head of department in a couple of schools. And then as we were going into that first lockdown, COVID, I had published a couple of videos on YouTube, and one of them kind of must have triggered the algorithm and took off a little bit. And so as we were coming into that first lockdown and suddenly I was at home, I thought I'll try and capitalize, and I made a couple more videos on quantum mechanics and like the history of quantum mechanics. And they did quite well. And then periodically I would kind of find some time to make videos, but I was doing this alongside a full-time head of department job in a school. So I was always trying to fit it alongside my main job. And that's why my release of videos has always been sporadic. But then in 2022, I applied for a job at the University of Liverpool as a lecturer in physics. And I was offered the job. So I left London and moved to Liverpool with my partner. And I started working at the University of Liverpool. And that's where I've been for the last 3 years. And that also ties into why for a couple of years I just disappeared off YouTube. And that's because I was focusing 100% of my attention on that academic job at the University of Liverpool. And I have more to tell you about that job and the future a little bit later. How can one build a career out of the things they love, like you? Would you say there's luck involved? And if yes, should that matter when it comes to whether or not one decides to pursue that? Okay, this is an excellent question. So what would I say? I would say that the most important thing when it comes to career is to think deeply about what you're passionate about. So start with what keeps you up at night? What do you think about when you wake up in the morning? What kind of ideas keep coming back to you in your mind? And what gives you joy? Like what type of knowledge, because there's a lot out there, what type of knowledge do you find it's easy to engage with, inspiring to discuss? What gets you excited? What gets you enthusiastic? Pay attention to that. And then the next phase is to develop expertise in that thing. Because what's going to be valued ultimately is the depth of your knowledge. Because by becoming an expert in something, you set yourself apart because you have now developed a scarce resource. That expertise is not possessed by everyone. And there will always be other people who value your expertise. So find the passion, develop the expertise, and then yes, there is always elements of luck required. Luck runs through everything in life. Some people are more lucky than others and life can be really hard. Some people get really horrible setbacks at an early age. Some people cruise through the first 50 years of their life without any setbacks. So this is just a fact about the universe and the world in which we live. But what you can do is, if you can cultivate a mindset where you believe in yourself, where you're enthusiastic and passionate about sharing your expertise with other people, then what you'll tend to find is that other people enjoy being around you because you're giving off those positive vibes, you're enthusiastic, you embody the enthusiasm for the knowledge that you then hope others will embody by receiving that knowledge, and people find that attractive. So yes, luck is an element, but if you can cultivate that mindset of self-belief, enthusiasm, and passionate articulation of the expertise that you possess, then I think you'll find that more opportunities will come along your way. So that would be my advice. What keeps you motivated to explore these ideas, and how do you decide the topic for each video? Okay, so that's a great question. What motivates me? Well, if I'm perfectly honest, I suppose there's two factors. First of all, there's the intrinsic motivation, and that comes through the process of learning new knowledge. I love understanding stuff, and I love feeling like that knowledge has become permanent in my brain. And when you approach a new topic in physics, often it requires a huge amount of work to try and wrestle with the ideas. You need to do research, read several different books, different articles. You're really trying to piece something together until finally it might click in your own brain. And then for me, the process of taking it from that stage where it's clicked in your brain to thinking about how to explain it and break it down so that other people can understand it, and then articulating that, expressing it, that process is where the knowledge really gets solidified. And I've always found this, that the best way of knowing whether you've understood something is asking yourself the question, can I explain it? And can I explain it clearly? And then if someone asks you a question, can I explain the answer to that question? Are you able to be agile with the knowledge rather than just memorize it and regurgitate it? So for me, whenever I make a video, I'm going through that process every time. And what I'm therefore doing is increasing the amount of knowledge that I have as a resource in my own mind. And so for me, I can't think of anything I'd rather do than just increase my knowledge of how the universe works. So I don't lack any motivation from that intrinsic perspective. But then the added bonus is when I started making these videos, I realized that other people benefited from my attempt to explain stuff. And so it brings me a huge amount of pleasure and joy knowing that when I make a video, there are all these people around the world who are benefiting in some way from that knowledge as well. So, I enjoy passing on the knowledge. So I'm not short of ideas. I have literally got a folder on my computer which has hundreds of video ideas. The issue is time and thinking about which of those videos I want to zoom in on and pay attention to. And often I would say that the things that kind of capture my attention are things that maybe are new to me, so things that I haven't necessarily studied in detail before, or when I take a topic that I already know, but I think of a way of seeing it from a different perspective, or I try to understand the history behind the idea, and that provides some new context. So I like the personal story. I like to have a narrative through the video, and if I can find that narrative, then I can feel very motivated, and I often make good progress, quick progress. More recently, I've been trying to do a bit more visualization. My very rudimentary coding skills have always limited what I could do in terms of those visual elements, but I've got a little bit better with that. So that can also be motivating at the moment. But you'll also find sometimes I'll progress through a video, it'll be 90% complete, and it's that last 10% which is often the hardest, because you need to watch, rewatch, check for errors, try and catch the mistakes, which are always inevitable. And you can I can kind of lose motivation a little bit at that final phase. And there are a number of videos which got to the 90% complete phase, and I just haven't done that last 10%. So I will try to get round to that. Do you consider making response comments videos on controversial topics of other YouTubers? So I'm open to new ideas. It's not something that I've really thought about in the past. As you probably noticed, my videos have tended to focus on well-established physics and trying to make those accessible by translating them into a form where if you've got basic knowledge of calculus, you can kind of follow along. That being said, I am going to be introducing some shorter form videos. I'm going to keep the longer form videos, but introduce some shorter form videos with me on camera where I discuss latest developments in the world of physics, some research articles that have been in the news, and also maybe thinking about topics that are broader than just physics. For example, the higher education landscape, culture of academia. And in those cases, I'm going to have some opinion. I'm going to have to get off the fence. And so you will see me having an opinion, but I'm always wary of stating my opinion with too much conviction, especially when I'm talking about a topic that I'm not an expert in. So I think it's easy to speak with conviction, and it can be quite convincing when someone speaks with conviction. But ultimately, I want to try and be careful that when I'm forming an opinion, it's an opinion that is based on evidence. So I will try my very best to keep intellectually honest if I do have opinions in future videos. What do you do outside YouTube? Why did you take such a long break from making videos and now you're more active than you've ever been? Well, as I mentioned earlier, so I am currently a senior lecturer in physics at the University of Liverpool. And the reason why I took a break for a few years was because when I started that job, it required my total 100% attention. I was starting a new university job in a new physics department. I was involved in establishing a new physics education research group at the university. I was supervising PhD students, master's degree students. I was lecturing an introductory quantum mechanics course, thermodynamics course. So I had my hands full. But then at the start of this year, I realized that number one, I was missing making the videos. And number two, I realized that they were actually incredibly valuable. And I'll have more to say about the value of academic output and the value of something like YouTube in future videos. But at the start of this year, I thought it would be a real shame to let that project, which I'd put so much love and passion into, to let it die. And so, as you've noticed, I started making videos from the start of 2025. And that has now led to a position where I will actually be leaving academia and leaving my university job on the 31st of July in 3 months' time. And I will be focusing full time on YouTube. So you're going to see more of me. You're going to see more of my videos. And I just wanted to tell you a little bit about that. So I'm going to stick with the long form content videos. I know a lot of you value the deeper dives. They're going to stay. But what I'm going to also do is hopefully introduce alongside those some shorter form 10-15 minute videos where I speak to camera, and as I mentioned, it could be about latest topics in the news, latest ideas in physics. It could be discussing more topical issues that expand beyond the realm of physics into science and into how science intersects with society, politics, and the political landscape. So I hope that will be something of interest to you. And with that in mind, given that I'm going to now focus 100% on YouTube, this is going to be my sole income. It's really important that I try to convince you that what I'm producing is of high value, so that you subscribe to the channel. So I'll be really grateful if you enjoy the content I'm making. Please hit the like, hit the subscribe button. And you'll also be pleased to know that I've finally got around to setting up a proper Patreon tier structure. You'll see the link in the description. I'll be really grateful if you could head over to Patreon, look at what's on offer. there are actually going to be perks to subscribing to different tiers. And I really want to try and help build a physics community where we can discuss ideas and I can engage with the community, engage with all of you, and share what I know, but also learn from you guys. Because honestly, it's amazing how you hold me to account in the videos, how you spot errors, how you ask brilliant questions. And moving forward, I really want to engage more with that. So I'll be really, really grateful if you're interested, if you're able. Please do head over to my Patreon account. Are there magnetic waves, magnetic frequencies, magnetic standing waves, or magnetic photons? Okay, so this is a really interesting question. So it turns out you can't have magnetic waves in isolation. So what we do have in the universe are what are known as electromagnetic waves. And an electromagnetic wave is a self-propagating oscillation in the electric and magnetic fields. And in fact, the oscillating electric field induces an oscillating magnetic field and vice versa. And this self-propagates, traveling at the speed of light. And this is what's called an electromagnetic wave. So you can't just have the magnetic wave on its own. Now, according to quantum mechanics, when you introduce quantum mechanics, then that electromagnetic field becomes quantized. And the smallest possible vibration of the electromagnetic field is what we call a photon. So a photon is the smallest vibration of the electromagnetic field, not just the electric part, not just the magnetic part. And then that means that when we think about the idea of, say, a magnetic photon, you're not going to find that in any book. We don't have just a magnetic photon. We have an electromagnetic excitation, and that excitation is what we call the photon. In terms of frequency, so the frequency of the magnetic component of the electromagnetic wave will be the same as the frequency of the electric component, or another way of saying that is an electromagnetic wave has a frequency and the magnetic and electric components have the same frequency. And then you can set up standing wave patterns of electromagnetic waves inside some kind of cavity. And I can imagine you could like focus in on the magnetic element of that. But as I've said, there's always an accompanying electric component and they're tied together intrinsically. One thing that's worth mentioning is that you can have in a crystal lattice, you can have what are known as quasi-particles called magnons. And a magnon is the quantum of a spin wave. And a spin wave you can think of as being a collective oscillation of aligned magnetic moments inside the crystal lattice. And this is a phenomenon we see in condensed matter physics. And that magnon travels like a particle with momentum and energy, but it's not a photon. It's not a magnetic photon. So I hope that answers that question. I've come at this point to the conclusion that a photon is just whatever I currently need it to be for my problem. I need a ground state excitation and momentum representation, bam, photon of a certain wavelength. I need a local energy carrier, bam, point particle photon. It's just a representation in whatever basis is useful. Is this a fair way to think about things? Also, what the hell is mass in quantum field theory? So yes, I think that's a very good way of thinking about things. Different representations for different purposes. So a photon is an excitation of the underlying quantum electromagnetic field. And in the quantum field theory framework, you have the vacuum state. And if you act with a creation operator on that vacuum state, then you can get a photon state. If you build using the momentum representation, then you can get a plane wave state for a photon. And if you then superpose lots of different plane wave states, you can get a localized wave packet essentially, which is localized in space and moves like a particle. And then you can also have different polarization basis states as well. So the way you described it, spot on. In terms of mass, well, the way I like to think about mass is effectively it's an intrinsic label that we attach to the quanta of a quantum field. That sounds very abstract. You can think of mass as essentially telling you how much energy is required to take the vacuum state into the lowest single particle state. Or another way of saying that is how much energy it costs to cause that smallest possible ripple in the underlying quantum field. So you can think of mass as being the invariant cost of creating a quantum of a particular quantum field at rest. If the universe is expanding as we observe at the galactic level, then doesn't this also exert a tiny but non-zero force at the atomic level? Well, that's a great question. The expansion of space affects all space, including on the smallest of scales. But the key point is at those small scales, say for example atomic or subatomic, local forces completely dominate. So if you think about an atom, you've got the positively charged nucleus and you've got the negatively charged electrons, and that electric force between those opposite charges is incredibly strong and completely dominates any expansive effect at that scale inside the atom. And likewise, strong nuclear force totally dominates. So these locally bound objects are essentially unaffected by the cosmic expansion of space. And yes, you could calculate the size of that cosmic expansion relative to, say, the attractive force between protons and electrons, and you can see that the electromagnetic force utterly dominates to such an extent that the effect of that cosmic expansion at that scale, it would be so negligible that it would be almost impossible to measure. How many dimensions do you think there are? I've heard different numbers from different people: 3, 4, 6, 10, infinite. I think M-theory poses 10, but I'd like to hear your thoughts on the validity of that number. So, excellent question. And yes, in popular science, lots of different numbers are thrown around. So let's start with why the number 3 might be mentioned. So 3 dimensions of space. You've got forwards, backwards, left, right, up, down. You can think of these as the classical Cartesian coordinates of space. And they're effectively the number of labels or pieces of information we need in order to locate an object in space once we've introduced some coordinate system. The reason you sometimes hear of 4 dimensions is because now we're introducing the 4th dimension of time. So we've got X, Y, Z, those are the 3 space dimensions, and now we introduce time, that's the 4th dimension. And the reason that these are sometimes grouped together is because of the development of Einstein's theory of special relativity and the unification of space and time. And this then is generalized in the general theory of relativity, where we understand that the presence of mass and energy in the universe affects the curvature or the geometry of the 4-dimensional space-time in which we exist. Now, string theory is a theory that's been put forward in order to attempt to unify quantum mechanics and Einstein's general theory of relativity. And very crudely speaking, the fundamental objects within string theory framework are vibrating filaments of energy, which are called strings. And these strings are tiny, like 10 to the minus 35 meters, very small, and they're vibrating. Now, if you try to take quantum mechanics, so classical quantum mechanics, if you think about it, is a theory of single particles. And according to the quantum mechanical framework, those single particles essentially have no spatial extent. Like an electron is effectively 0-dimensional. It's a point which we attach labels to, and that those labels tell you about how that point particle interacts with others. What string theory does is it says, what if we take that fundamental 0-dimensional object, and let's just imagine it has one spatial dimension. Let's imagine that it's extended along one spatial dimension. And now let's make it consistent with the laws of quantum mechanics. Let's enforce the rules of quantum mechanics on this one-dimensional extended object. Now, if you do that, in order for the theory to be consistent with quantum mechanics, certain constraints are placed on the theory. And one of those constraints is that your string has to be oscillating or vibrating in a 10-dimensional space-time. So that's 1 dimension of time, Then you've got what we'd normally consider the three large dimensions of space, x, y, z, and then you've got these 6 extra spatial dimensions. Now we don't observe those, so where are they? Well, according to string theory, the string theorists would say that those 6 dimensions are compactified. So they're effectively squashed up and wrapped up into special geometries. You might have heard of Calabi-Yau manifolds, certain shapes of 6-dimensional space, and the strings then vibrate because they're very small. They can see these extra dimensions, they vibrate, and how they vibrate in those extra dimensions determines the properties that we then observe at the macroscopic scale, very crudely speaking. So yeah, string theory predicts that there are 10 dimensions of space-time. And then M theory is a generalization of string theory because it turned out that there are actually different versions of string theory. And M theory is kind of an overarching framework which shows that there are connections between these different string theories. And this more general framework includes an extra dimension of space. So in M theory, the fundamental entities aren't strings, they're things called membranes. And we now have one extra space dimension. So we have 11-dimensional space-time. Now, which of these are true? Well, let's think about it. At this moment in time, there's 0 experimental evidence for extra dimensions. These are just purely theoretical constructs that exist within these frameworks of string theory and M theory. Only time will tell whether the elegance of that mathematical framework actually relates and corresponds to reality, what we actually observe. Anyway, I think that will do it for now. I just wanted to thank you once again for 250,000 subscribers. Honestly, I can't believe it when I started this channel that it would ever get to this stage. But I just wanted to thank each and every one of you for your continued support. And I really look forward to sharing some of my new projects with you over the coming weeks. So until next time, goodbye.